Hello, I'll be doing my second video on energy and oh, rates, because I feel like it. Actually, no, because it's kind of hard as well. It's a big topic, kind of, because like there's graphs and everything. First question says a reusable heat pack usually contains sodium acetate. Describe how these heat packs work and why they are recharged by heating in boiling water. In your answer, include reaction profile diagrams and equations where appropriate. Okay, so basically, how these packs work is there's no chemical reactions. It's just a physical, like, state change. So basically, in the packs, the liquid sodium acetate turns into a solid. Okay, so a liquid turns into a solid, so that's freezing. So how do you freeze something? You take like you take heat energy from it, so which means it's exothermic because it's giving out heat, so it's cooling itself, so it's turning into solid. So which means uh, turning solid, releasing heat because the oh, physical physical change is exothermic, so it's giving thermic, so it's giving out heat. And when the to recharge the solid, acetate turns back into liquid liquid it'll be gaining it'll be gaining heat from the water, yeah, gaining heat since it's like kind of like melting in heat as it is an endothermic reaction. Okay, physical reaction, sure. And then it won't include reaction profile diagrams and equations where appropriate. So basically, the equation is it's just solid sodium acetate, yeah, acetate. When it's like turns sodium liquid turns into solid, solid plus plus heat, and it's losing heat on it by itself by giving out heat. And so this is using pack pack a recharge. Okay, so NiCH3COO, solid plus heat can go back to NaCH aqueous, and heat is gained, so it's bigger than 0. And so for the diagrams, we can have a enthalpy, and this is reaction process. And let me copy that because we're gonna. So this is when using pack, and then we'll have another one. Okay. Well, this is when recharging. Okay, so basically the energy is lost. So that's activation energy. And that's the change in heat. Okay, and then for the other one, I mean, we can just write this here, but like seeps. Not seeps. I mean, kind of. You do have to do it, but I'm just not doing it. Yeah, and then that's the change in H right there. So that's it for this question, and we'll move on to the next question, which says that when carbon monoxide reacts with oxygen to produce carbon dioxide. Okay. Well, okay, I'll read the whole thing. When carbon monoxide reacts with oxygen to produce carbon dioxide, 566 kilojoules of energy is produced per mole of oxygen gas consumed. And part A says to write a balanced equation for the reaction. So carbon monoxide plus oxygen gas, carbon dioxide. And well, we have to balance it. There's a single O. We can't have that because it's oxygen's all even here. But there's two carbons, so I just have to double that. And now there's four O's, and that's balanced. And they're all gas. And then now, for the energy, well, energy, there's more energy here, and there's less energy here because you're adding, wait, energy is produced per mole of oxygen gas consumed. So energy is produced to give to the outside, so itself is actually losing. So it's negative 566 kilojoules. And for part B, it says draw a reaction profile diagram for this reaction given the activation energy for the reaction is 250 kilojoules. Okay. So it's still enthalpy. And this is reaction progress. And now basically, because it's a lose, it'll be like, actually, wait. All right. EA equals, what's 250 kilojoules, and then delta H equals negative 566 kilojoules. And basically here is 2CO gas plus oxygen 2 gas, and here will be 2CO2 gas. That's basically it. And for part C, just annotate the reaction profile diagram to show the impact of adding a catalyst to the reaction. Okay, so it's basically gonna look like, okay. Because catalysts produce a alternative path for with a lower activation energy. And for part D, list two other ways of increasing the rate of this reaction. Explain how they cause the increase. So, two other ways are increasing temperature and pressure. I mean, these are just the generic explanations. I'm not writing. It's too much. So basically, temperature is because it will increase the kinetic energy, the average kinetic energy of the particles, which means it's easier. Okay, it's a higher frequency of collisions because they're moving faster, and that will increase the rate of the reaction as a larger proportion of the particles will reach the activation energy. And for the pressure, well, the volume is decreased. Okay, the volume is decreased in order to increase the pressure. So, which means the particles are closer together, increasing the frequency of collisions again, and uh, which is increase the rate of reactions as a larger proportion of particles will reach the activation energy by colliding with more successful collisions. And pressure can only be used when there's gases in the equation, like only gases, which is happening right now, so I can use pressure. These are three easy ones. Okay, yeah. All right, that's basically it. I'll just write it down if it's in like a actual assessment. Oh well. Bye bye.